Hello, welcome back to three-phase circuit analysis. We're doing Y-delta problems. This is kind of a monster problem a little bit. Once we do it, you'll be able to understand where the steps involved and it won't seem so bad. But at first, the first time you see one of these problems is a little daunting, and that's why I wanted to show you this. So let's just read it. We'll have to draw some things. We'll have to talk about some things. But this is a good test question. So we have a balanced delta load that has an impedance of 216J63. That's a delta load. And it's connected in parallel with a Y load that has an impedance of 50 and an angle of 0 ohms. Right there, that first sentence seems weird, because not only do you have a delta load, but you also have a Y load, and those two loads are connected in parallel. So we've never done a problem like this before. We did do a problem a while back where one leg of the delta load had like a little tiny parallel part. This is different. This is saying we have an entire delta triangle and an entire Y-connected load. Those two loads are physically connected in parallel to the transmission line. That's what that's saying. Okay? The delta load is fed from a line of impedance, here we go, 0.5 plus J4. That's easy. That's just a line impedance. And then it's telling us the magnitude of the line to neutral voltage of the Y load is 750 volts. So again, that's kind of a weird, because you have two loads to think about, it's weird. But if you think about it, if you just ignore the delta load for a second, just pretend there's no delta load at all. If this were just a YY circuit, then this makes sense. The magnitude of the line to neutral voltage of the Y load, we could draw a single phase equivalent circuit, we could figure out what the line to neutral voltage is, and that the magnitude of it's 750. Notice they don't give us a phase angle, and they don't tell us to take anything as a reference. So we're just given the magnitude. We're going to have to make some assumptions along the way to solve this problem. All right. Now we have four things we want to find, and every one of them is just to find the magnitude of something. So when I told you the rule of thumb before, in a problem when it just tells you find the magnitude of something, two things you need to think about. Number one, you probably weren't given enough phase information to begin with to be able to find the full phasor representation of all the stuff we're trying to find. So that you're probably going to have some information missing from the problem, and in fact we do. We don't know if we don't know the phase of this voltage, for instance. So we have to make some assumptions. And number two, you're going to you need to, when you do your calculations, you make whatever assumptions you can and carry your complex numbers down all the way as far as you can to the end. Don't start throwing phase information away from your impedances and stuff, because some people think, well, if I only care about magnitudes in the end, I'm just going to find the magnitude of these impedances and just use that. Don't do that. You got to keep the complex number arrangement of everything intact. Make an assumption here at 0 degrees if that's what you have to do. Carry your complex number calculations to the end. Then at the end, throw the phase away and just keep the magnitude and circle the magnitude. That's going to be a lot more bulletproof than trying to figure out what you can throw away and what you can't in your problem statement. All right, so we have a parallel combination of two weird-looking loads. And then what do we ask to find? The magnitude of the line current feeding the loads. Okay, so we have a transmission line. It's going to be feeding two loads. We want to find the line currents. We want to find the magnitude of the phase current in the delta load. These are the currents that are circulating in the triangle, the phase currents. And then we want to find the magnitude of the phase currents in the Y load. These are the currents that are going through each leg of the Y load. And then we want to find the magnitude of the line voltage at the sending end of the line. In other words, there's a generator here somewhere off on the left-hand side of the circuit, and we want to find the line voltage, VAB, VBC, VCA. We want to find the magnitude of those guys. Of course, the magnitude will all be the same for the three different line voltages, but in other words, we don't care about the phase. We just want to know what the magnitude is. Okay. The other thing that jumps out at you right away when you look at this problem is you're given the delta impedance, each leg of the delta triangle in rectangular form, but you're given the Y load impedance as a weird thing. Usually you don't see impedances as magnitude of phase, but you can convert this to rectangular. And what is it, by the way? If you have 50 as a magnitude at an angle of 0 degrees, that means that impedance lies on the x-axis. Which means what? It means it's real. There's no imaginary part to it. If the angle is 0 for the impedance, there is no imaginary part. It's not up and down. It's just completely horizontal. That means that this is a fancy way of writing 50 ohms. You see, this is a great trick that a professor might throw at you and say, give you this, and people might freak out and say, whoa, I've never seen a phase like that. This is just basically, I could have rewritten it and said, hey, it has a Y impedance of 50 ohms. Well, that's boring, but this makes you think a little bit more. What does this mean? It means 50 angle 0 means 50 ohms. No imaginary part, no inductance, no capacitance for that part. So I know I said first that you always want to write a single phase equivalent circuit first, but in this case, because you have a parallel combination of two weird loads, the first thing you should do is draw that. So in your head, you can see what you're actually looking at. So it's going to be a little weird, but we're going to do that over here. And then after that, we're going to, almost immediately after that, we're going to write the single phase equivalent of that. So it says we have a balanced delta load, and we know the impedance in the load. So let's start there and just draw a delta load, right? And we know it's going to have a resistive component and an inductive component. So I could draw it as boxes. That's fine, but I'm going to go ahead and draw it as a resistive and inductive component just to be different this time. And then this leg is going to have a resistive and an inductive component. And then here we're going to have a resistive and inductive component, like this. All right, and we're going to do some labeling. It's 216J63. I'm only going to label it one time. So this is going to be 216 ohms, J63. Is that right? 63, yeah, ohms. I'm not going to label them here and here and here and here. You know that these are all the same. I'm just trying to keep the drawing from being uncluttered. This is what we call the A terminal, capital A. This is the capital B terminal. This is the capital C terminal. I'll put some dots there if that makes you happy. All right. Now, if there was no parallel combination of anything, then we would have a balanced delta load, and we'd be connected. It's in parallel. Forget about that for a second. Then it says it's fed from a line of impedance 0.5 plus J4. So let's go ahead and draw that part before we do anything else. It'll be easier to wrap your brain around. So let's go over here, way over here, and I'll draw the inductive component here and the resistive component of the transmission line right there. Make sure you understand what that is. And then we will go and do the exact same thing here. We'll draw the inductive component of the transmission line right here, and then we'll come down here and we'll do the exact same thing. This guy has inductive and resistive component here. And we're going to label on the other side of the transmission line, this will be little a, little b, little c. Somewhere to the left of this is the generator, but we don't know anything about the generator in this problem, so we don't write anything. And it tells us the transmission line is 0.5 plus J4. So I'm going to label it only one time, like this. So you know that this is the same as this and this, but I'm not going to write it down because it gets cumbersome. So we have a balanced delta load. It has an impedance. We have a transmission line driving it. It has an impedance. Now, the middle part of the problem is where it gets confusing. We haven't done a problem like this. This delta load is connected in parallel with a Y load, and we're given that impedance of the Y load. So let's go and draw it as best we could. If we were going to actually, what does it mean to be in parallel with something? It means the three lines that are feeding this triangle also come and feed something else down here. That means the load down here is completely in parallel with the load up there. So if I were going to do that, I would literally write a connection there. Of course, I would cross over this wire, cross over this wire, and I would come, let's see here, I'm going to do this over here. And this guy has a resistive component. And just for completeness, I'll put an inductive component, but I know it's 0 there. And in fact, I'm going to go ahead and write that right now. So this is 50 ohms. And this is J0 ohms. So this is nothing, but it's basically 50 ohms. Now this is a Y-connected guy. So how's this going to look? This Y guy is going to come, and we're going to have a common terminal right here, and we're going to have an inductive component for the B phase and a resistive component for the C phase. Where for the B, this is all for the B phase. Where is this going to connect? It's going to connect right here at the B line. And then since this is Y, we're going to have something like this, and where is this going to connect? It's going to connect right here at the C phase. Now you can see how this looks, that it's two completely different loads connected in parallel. And let me go ahead and do some labeling. This is, you know, I have A, B, and C labeled here, but I can also label them here, probably right here. A, capital B, and capital C. These are the same A, B's, and C's that are labeled up here. It's the exact same points. I could have, if I had a larger board, I could have this, and I could have this entire Y circuit over to the right, but then I'd have to draw a bunch of arrows and a bunch of lines connecting everything and look weird. I think it looks a little bit clearer to have the delta load, and then you have hanging off from the same 3 transmission lines a Y load. So you have a common terminal here, so you know this is a Y load, and we want to label that common terminal, as we always do, capital N. That's the neutral terminal there. And that's basically the drawing. And unfortunately, that took almost the entire board. I guess I could have saved some space here. What do I want to do next? I think what I want to do, yeah, make sure you understand this. Oh, this this 50 J0, make sure you understand that that's the exact same thing as magnitude 50 at an angle of 0 degrees. You can do cosine 0 plus J sine 0, and you can convince yourself that it's just a real number. I just went ahead and did this for completeness. I really could have left the inductive part out completely. It's in fact labeled to be 0 there. So now that we have the drawing and we kind of know what it looks like, sort of, let's look at part A. We want to find the magnitude of the line current feeding the load. That just means we want this line current here. So let's call this AA. IAA. Whatever AA is, we're asked to find only the magnitude of it. So once we know the magnitude of AA, that's the exact same as the magnitude of BB, which is the exact same as the magnitude of CC, because they're 3-phase circuits and they're balanced. So the magnitude of a 3-phase triplet is always the same. So whatever we find for this one, we don't have to add and subtract 120 because we're not even asked for the phase. We only want the magnitude anyway. So the way to proceed here is to draw a single-phase equivalent circuit as best we can for this. Now, I know that you know if we were drawing a single-phase equivalent just of the Y load, like if the delta wasn't here, your single-phase equivalent would have this impedance, and then it would have this impedance, and the neutral would come right back around, and that would be the answer. Okay? But that is true, that's going to be part of our single-phase equivalent. But that is in parallel with this. So what we need to do is take this impedance, transform it to a Y load. How do we do that? By dividing by 3, right? We'll get an equivalent Y impedance for this. And so what we'll have for our single-phase equivalent is we'll have the line impedance, and then we'll have an impedance here, which will be this transformed impedance. And in parallel with that, we'll have this impedance hanging off the other end. So let's go ahead and draw that. And it's going to look weird because we haven't done a problem like this, but this is how we're going to solve this problem. So the first thing we need to do is we need to find the equivalent impedance ZY. That's going to be this impedance, which is 216 plus J63, and we're going to divide by 3. And what do we get when we do that? We get 72 plus J21 ohms. So this is what this delta load would look like. If I reformulated the problem and I said there's a Y load in parallel with another Y load, that impedance that we just calculated would be what would look like this, or what would be equivalent to that. So let's go ahead and write our single-phase equivalent circuit. What we have is we have some generator over here, which we don't know anything about because we're not given any information about it. We come out of this guy to terminal A, but then we have a line, which is a resistance and an inductance. And then we have another guy. Let's go ahead and label all this so far. The line impedance is 0.5 and J4. And this is little a and this is big A, flanking each side of the transmission line. Then, what do we have? We have this delta load, but in order to do it as a single-phase equivalent, we transformed it to a Y load, so we have this impedance, which we just calculated there, which is a resistor and an inductor, like this. And let's go ahead and wrap it around, like this. And we have, let's put little, yeah, let's label this over here, because this is a Y generator. This is little n over here, little n, where the other phases of the generators connect to the common point. And what do we have for this? We already found what this is. This is 72 and J21. This is the transformed impedance, equivalent Y impedance for the delta load. Now, if there was no Y load at all, no Y load, nothing in parallel, it was just delta load, this would be our single-phase equivalent circuit. We have a line impedance, we have an equivalent load impedance. This is what we've been doing like in the last problem. But in parallel with this, which we now have as in our circuit, we have something hanging off the same exact transmission line. So on the other side of this thing, we have this, which is just 50 ohms. So in parallel with this, you have a single resistor. And what is it going to be labeled? It's going to be 50 ohms. Okay? Now, this guy is a real Y circuit, and this guy is a delta, which we're faking out and treating it as a Y equivalent. But this Y guy has a neutral terminal, capital N, and this guy, even though we don't really have a neutral terminal in the real circuit that we built, but equivalently, when we model it as its Y equivalent over there, it also has a neutral terminal, which is exact same terminal. And notice that they're tied together right here. So what we're going to do is we're going to put I like to do it in another color. This is capital N over here. So this, and let me label one more thing before we say that. This guy, we're going to call I little a big A. This is the single phase equivalent circuit for this problem. To be 100% honest with you, getting this right, and this is why I wanted to do this problem, because it's not obvious, right, at first. Getting this right is probably 75 to 80% of this problem, right? Knowing that you have a generator and you have a line impedance, knowing that you have to transform that delta load into a Y equivalent, knowing that you write the single phase equivalent like this, and in parallel with this guy that we just wrote, you have the other load, knowing that you have a neutral terminal down here, which is common to both. Even though this is faked out and this is just a mathematical tool, for all practical purposes, it is a Y circuit, so it has a neutral terminal, which is the same exact neutral terminal here. If I had built this as a Y terminal, I would have a neutral, which would be, in a single phase equivalent circuit land, the exact same place as tied together here. So now we have some progress that we can make, because what are we trying to do for part A? What is the magnitude of the line current feeding the load? It's difficult to see what to do here, but once we transformed everything and we have it in place here, we have a lot easier time with it, right? Because now we see we have a current going here, which is splitting here and splitting here. So this current is just this is just a parallel guide, and then it recombines and goes back like this. Now the other part of the problem that we haven't talked about yet, which we're going to need to do this part of the problem, is it says the magnitude of the line to neutral voltage at the Y load is 750. The magnitude of the line to neutral at the Y load is 750. Okay, let me write a couple of things down. I guess we'll do it like this. Given in the problem statement, the magnitude of the line to neutral at the Y load, AN, right? This is magnitude A is way over here. Magnitude line to neutral is 750. So that's crucial because it gives you the voltage across this, and because it's in parallel, it also gives you the voltage across this. This is something that's not too easy to see from the full-blown circuit diagram where everything's hanging off and you have three phases and one of them's a triangle and one of them's a Y. It's difficult to see that because, in fact, you can't see it because this guy here is built as a triangle with no neutral terminal at all. But we know from equivalency when we write it as a Y, it's going to have a neutral terminal, which will be in parallel with this one. So what you're given in the problem statement is crucial. It's telling you the voltage across this 50 ohm resistor, and it's also telling you the voltage across this leg of the load, which is not real, but it's equivalent. It's how we're solving the problem. And once we know these two currents, we add them together, which gives us this current, because of course it has to split according to Kirchhoff current law. All right. So I'm going to write a couple things down. This is the Y load, which I know you know, but I just don't want you to forget. And this is the transformed delta load, just so you don't forget what everything is. Okay. Now the next thing we're going to do is actually figure out what this current is. So that's what we're trying to find. So we want to find the magnitude of IAA. We want to find the magnitude of IAA. So that's going to be the magnitude of the following things. We're going to have VAN over, VAN is this voltage over this impedance, 72 plus J21 plus magnitude VAN over 50. Make sure you understand that. In other words, I know the voltage, I know the magnitude of it anyway. The magnitude across this, voltage divided by impedance, this gives me the current through this leg. That's what this is. The same voltage divided by this gives us the current through this leg right here. I add them together, which is going to give me the total current flowing through both of those legs, but I'm taking only the magnitude of the answer because I was only given the magnitude of this to begin with. And that's going to give me the magnitude here. So when you actually stick 750 here, let's go ahead and write it down. It's going to be 750 over 72 plus J21 plus 750 over 50. All right, I want to tell you a couple things about how this works. When you stick 750 in your calculator with no phase angle, even if you don't put any phase angle, if you just stick it as a real number, think about what a real number is. It's a complex number with an angle of 0. We already said that actually for the 50 ohms at an angle of 0. You can write anything as a complex number, right? So when you actually stick this in your calculator as 750 with no phase at all, and you divide by this number and you do this and divide by this number, the calculator is just going to treat it as 750 at an angle of 0, 750 at an angle of 0. So I guess what I'm trying to say is when you put real numbers in your calculator and do this divide by complex numbers like this, it's going to treat it as an angle of 0 anyway. So you're going to get a magnitude phase answer out of it, right? That's why we have the absolute value bars around it. We don't really know if this is 0 degrees or not. We don't know if it's the reference of the circuit. It doesn't tell us. But for the purpose of the calculation, what we're doing is we're basically saying 750, the voltage here, is sort of the reference right now anyway. But at the end of the day, once we calculate the answer, we're going to get a phase angle in part of our answer, but we're just going to throw it away anyway because we're only asked for the magnitude of the current here. So whenever you do this, what you're going to get is, inside here, when you do this division, you're going to get 9.6 minus J 2.8 plus, and you're going to get 15 for the other part over there. And so what you're going to get is, you're going to get magnitude. When you add these guys together, let me see here, hang on a second. Yeah, you're going to get magnitude 2476, angle negative 6.49. So this would be, if I actually told you that this was 750 at an angle of 0, if I knew the full phasor and that was actually it, then the current IAA would actually be exactly equal to this entire phasor. But because it only tells us this is what the magnitude is, not only do I not tell you to assume the phase, I don't actually know the phase at all. I haven't measured it. I just know somebody told me off the truck somewhere that the magnitude of the line voltage was X, which is 750. So this would be the full-blown answer, but since I really don't know that that's actually the phase angle of 0, then they're asking me for only a magnitude. So what you say is the magnitude of the current, AA, is 24.76 amps RMS. And that's the answer. So you see what I mean by about 80% of this problem is just drawing this diagram properly, because once you have it drawn, and once you know the voltage here, well, it's very simple. Voltage drop across this gives me current. Voltage drop across this gives me current. Add the currents together. Boom. I get a total current here, AA, and I'm just taking the magnitude of it, which gives me 24.76. I don't need to do anything for phase B and phase C because they also have the same magnitudes, and I'm not asked to find those anyway. So the magnitude of the line current feeding the loads, that's done. Part B, what is the magnitude of the phase current in the delta load? In my opinion, part B is the most difficult part of the problem here, not because the math is hard, but because you have to just think about it a little bit harder. What I want to know is I want to know the magnitude only of the phase current in the delta load. In other words, I have a triangle here. This is the phase current, IAB. This is another current, BC. This is another current, CA. The magnitudes of all of these three currents are all going to be the same. The phase angles will differ by 120, you know that. But that's what I want. I want this right here. I want this right here. I want this right here. The same number, the same magnitude is going to be true for all three of them. However, in order to make any progress at all in this problem, we had to take this and transform it into a Y equivalent, which is what's here. This impedance is not what's in the problem. This is some equivalency thing that helps us find the line current. So the question is, how do I find this? How do I find the current through here, right? How do I find the current through here? There's probably a million different ways to do this problem. I'm not going to lie to you. There is a million ways to do this problem. But the way I did it was the following. Pretend for a second that there is no resistive load hanging off of this thing. I know the voltage across this guy. I already actually said it's 750. If I calculate the current through it, right? If I calculate the current through this Y load here, then that is not really really the current through the actual load of my triangle because this impedance isn't actually in the triangle. This is a transformed quantity, okay? But if I can figure out what the current, let me see how I can explain this a little bit more, I'm wrapping myself around the axle to see how I can explain this a little bit more clearly. In our actual problem, we have figured out, because of the combination of all this stuff, we figured out the line current is 24 point something amps. That's what it is, okay? But if, let me think about the best way to do this. How would I find the phase current through this? Here's how we do it. Here's how I get the point across to you. How would I do this problem? How would I find the phase current in the triangle if there were no load over here at all and I knew the voltage across this? How would I do it? I would say, well, the voltage divided by this impedance, this fake impedance, is some number. And I would say that current is the same as the line current. Like, pretend in another universe this problem is different and it was just a single delta load, right? I would have transformed it. I would have gotten this guy. If I know the voltage across it, I would find the current through this fake delta load, which would be the same as the line current, right? The line current is what the key to finding it, because when you have delta loads, if I know the line current, I can transform it to the phase current by the square root of 3 rule. So if there was no other loads hanging off of anything, the real secret to finding the phase current would be figure out what that current is through the load here, which is the same as the line current. And once I know that line current, I shift it with the square root of 3. That gives me the phase current, okay? But this problem is a little harder to see through all of that stuff because you already have a line current here, so you might be thinking, well, I'll just shift this. But that's not really going to give me the phase current here because I have a whole other thing hanging over here. So here's what you have to do to actually do it. You calculate the component of the current flowing through this fake load here, this equivalency load, and then you pretend for a second that this were the line current, because if everything else were gone, this would be the line current. And you take that current and you shift it with the square root of 3 rule. That's going to give you the phase current through this load. All right? Let's go ahead and do it, and then at the end we'll kind of sum it up and kind of repeat everything again to make sure you understand. In fact, we did that as part of the calculation here. What is the current through this leg? Let me call it magnitude of I leg through that guy. We actually did it as part of this calculation here. It's going to be 750 over 72 plus J21. Whoops. Yeah, J21, like this. Which means that it's going to be the magnitude of 10 at an angle of negative 1626. Okay? So the magnitude of the current going through that leg is just going to be equal to 10 amps, the magnitude. So the magnitude going through here is 10 amps of current. If there were no other load here, and if there was no other parallel anything, if it was just a delta circuit, then this current going through here would be the line current. It would be the line current. And then, since I know that I can shift between line currents and phase currents, what I would do is I would use the square root of 3 rule, which is line current, in words, is square root of 3 times whatever the phase current is. And I'm going to shift by negative or positive 30. Now, I don't know the phase sequence of this drawing. I don't know anything. But it doesn't really matter because all I care about is the magnitude anyway. So what I'm going to do is I'm going to say the magnitude of the line current, well, let's do it like this. Let's not erase this stuff. Let's not erase this stuff. We're going to say the magnitude of the line current is equal to the square root of 3 times the magnitude of the phase current. Magnitude of the phase current is what I'm actually trying to find. In other words, if I take the magnitude of both sides, this phase angle isn't going to matter. I'm throwing away the phase angle anyway, is what I'm trying to say. Now I know that the quote-unquote line current here, if this were the only game in town, would be 10 amps. So I stick 10 over here, and I say square root of 3 times magnitude of I phi. So what you find is the magnitude of I phi is equal to 10 divided by the square root of 3, which is 5.77. Okay, so what did we ask? What were we asked to find? Magnitude of the phase current in the delta load. We found the magnitude of the phase current, which is 5.77 amps, but it's worth repeating one more time to make sure you understand. If it was just a single delta load, What I would have done is I would have done this division by 3 just like I did in this problem. I would have put it here in the single phase equivalent, but I wouldn't have this here. I would only have a line impedance and a load impedance. If I knew the voltage across it, which is what I'm given in this problem, then I would find the current through this just by Ohm's law. Once I knew that current, that would be the same thing as the line current here. And I know how to shift between line currents and phase currents for delta loads. So I would have used that square root of 3 rule to shift, and I would plug in the line current, and then I would find the phase current. The only thing that you have to conceptually understand here is that this line current that I actually have in the problem cannot be used to shift and give me the phase current, because this line current is the sum of the currents going through this and through this. So because you have the parallel load, the line current that's actually in this drawing, which I found before, it can't be used to shift to give me just this delta current, because this line current is the sum of this current and this current. So you have to kind of think about it as components of phasors. That's a good, or components of vectors. You have a vector like this. You have an x component and you have some y component, right? And you can represent that phasor as those two numbers. Those two numbers describe the x component direction and the y component direction. I break it up into two parts. So if I'm talking about motion of a baseball, I can talk about the horizontal motion and do the equations in the x direction, and I can talk about the vertical motion and do the equations in the y direction. I can completely decouple the two things, and I can do an x analysis, and I can also do a y analysis. Well, I'm doing the same thing here. There's a total line current here, but it's the sum of two components. The component of the current going through here and the component of the current going through here, right? So whenever I find this current here, I'm basically finding how much of the line current comes from this load, or kind of goes into this load. I'm finding how much of it goes through there. So then if I just take that smaller line current, then I can shift it and give me my phase current, just as if nothing else was there. I'm pretending nothing else is there. How much of it is due to this, and I shift it. So I take that guy, I find out how much is going through that leg. This is what I get, and then I take this, and you could take the whole phasor if you wanted to and stick it in there. You can multiply or add or subtract by 30 degrees, fine, no problem. But at the end of the day, you're throwing the angle away anyway. So then you shift it using this guy dividing by the square root of 3, and you get 5.77 amps. That's about as good as I can do with that. It's a little confusing to think about, but that's how you have to do it. Now, it turns out that the next part of the problem is much easier, because the magnitude of the phase current in the Y load is much, much, much easier to figure out, because for the Y load, the current going through this 50 ohm resistor really is the phase current. Think about it. We have our drawing here. The current going through here, this really is the phase current. But I was given VAN. I was given this as 750 volts. Look at it over here if you want. 750 volts here. So the current through the 50 ohms, that by definition already is the phase current. So the way you write that down is you could say the magnitude of the phase current for the Y load, however you want to denote it, is just going to be equal to VAN over 50 ohm, which is 750 over 50 ohm. So the I phase current in the Y direction for the Y load is 15 amps. There's no shifting that's required here, because the actual current that I find through here is the actual current through the Y load, right? Because that's why it's so easy to do Y analysis with currents, because the current that goes through the load, that is the phase current. But it's different here because the current flowing through this fictitious load is not the actual current going through the triangle, so we have to do the shift, right? All right, so that's about all I can say about that. Let's do the last part of the problem. What is the magnitude of the line voltage at the sending end of the line? Sending end of the line. Line voltage. When you see line voltage, it means line to line voltage. So what you want is VAB. You want the magnitude of it though, VAB. So what you want to do is you want to try to calculate as much as you can with the complex numbers and then throw away the phase at the end. You want to find VAB. So it's helpful again to go back to our single phase equivalent. There is no VAB on this diagram, but you go back to the source end and you say, well, wait, if I can find VAN, the line to neutral voltage, this is a Y circuit over here, line to neutral, then I can do the square root of 3 shift to find VAB. So how do I find VAN? Well, I know this current. It's given right here, actually. I already calculated. It's 24.76 amps. But actually, if you look more carefully, when we did the calculation for this current, well, let me back up for a second. We know this current, so it's the current times this impedance gives us the drop here. Once I'm to this point, I know VAN is 750. That was given in the problem statement. So if I add this voltage drop to this voltage drop, that gives me VAN. All right, so that's what I have to do. So what you want to do, though, is you don't want to start throwing away phase information too early. We calculated IAA by taking the voltage divided by this voltage divided by the impedance, this voltage divided by the impedance, and then we had the magnitude of this phasor here. Then we threw the phase information away because we're only asked to find the magnitude in this part of the problem statement. When we're going through it here and we're multiplying this times the impedance to find the voltage drops, we want to use as much phase information as we can. We kind of implicitly assuming that this is a 0 degree phase angle here when we did the calculation. Use this with the phase information, times this impedance, and then we'll have another drop there. So let's write the equation down. You'll see what I'm saying. So V little an is the line current AA times, I'm going to write it as Z line so you understand, plus 750. Okay, the 750 is the voltage drop from here to here, and then IAA Z line is this one. So this is going to be this phasor. This is going to be, of course, what it's there, and then we're just going to add the 750 to that. All right, so then what we have is VAN. IAA is 2476, angle negative 649. And again, this phase may not be totally true. We're kind of assuming a 0 degree phase for our 750 that we were given. The line impedance, 0.5 plus J4. And then we have the 750 drop on the other side. So let's multiply these things out. AN times this, and you add the 750, you'll get 779.55, angle 7.15. Again, we don't really know this phase is 100% true, but we carry the phase information down to the end, and then we throw it away. Then we have our transformation rule, because once we have VAN, we shift using the voltage shift to VAB. So VAB is equal to the square root of 3 times VAN, and you have plus or minus 30 degrees. And again, you might say, what do I choose, plus or minus 30 degrees? But then you realize, no matter what I choose, it doesn't matter. All that's going to happen is I'm going to take this phasor here, and I'm either going to add 30 or subtract 30, but no matter what I do, I'm going to throw the phase away at the end. Anyway, I'm going to throw it in the trash can. So we carry it all the way to the end, and then you get to that last calculation, you realize it doesn't matter what this angle is or what this angle is because I'm throwing it away anyway. So the way you would write it down in your paper is magnitude of VAB, because now we're getting the answer. We're saying here's the magnitude, is going to be the square root of 3 times the magnitude of this, 77955. So magnitude VAB is 1350.22. Okay, that is this problem. It's a little bit of a doozy, but it's a good problem because it's a tricky problem, and it's something that you're probably going to be asked on a test at some point. Because as I've said many times before, when you do these three-phase problems enough, a lot of the problems seem real similar after a while, so this is a good way to confuse you. So here we have a delta load in parallel with the Y loads. We had to know to draw a delta load in parallel with a Y load. We have to know how to do that first. We had a line impedance. We knew the impedance of the delta load, and we knew the impedance of the Y load. Part A was to find the line current here, feeding everything. So the first step is to find the single-phase equivalent circuit. We take the delta, divide by 3. We get this fictitious, fake, imaginary equivalent Y load here for the transformed delta load. In parallel with that, we have the Y load. And then in order to find this current, what we did is we took the voltage that was given to us across this, divided it, across this, divided it, add them together, take the magnitude. This is the magnitude of the line current. Then for part B, the magnitude of the phase current in the delta load. What we did is we said, well, I'm just going to find the current through here, and I'm going to pretend that that part of this line current is what I would have if nothing else were present. So that I'm going to transform and shift using the square root of 3 rule. I go ahead and do the division. I find the line current, the the current through this leg in my single-phase equivalent. If nothing else were present, this would be the line current, which I would then shift, and so that's what I'm going to do. So I just go and do the shift by plugging in the value of the line current, which I just found, and then I find the phase current from it, which is 5.7 amps. The next question is even easier. It's what is the phase current through the Y leg of the load, which is through this guy. So it's just V over R, because that current actually is the phase current already without any shifting. I get 15 amps. And then the last part is finding VAB. So what I do is I say, well, I have a voltage drop here and a voltage drop here. I'm going to add them together. Voltage drop here across the line, voltage drop across the loads. VAN is given by this, and then I'm going to use the shifting formula to find VAB. So, lots of problems, and we've done a lot of material up to this point. Way back when we learned YY circuits. Then we learned Y delta circuits, and we've done a lot of problems figuring out how to do that. Now the next step of your journey in balanced three-phase circuits is what happens at the source end whenever we change it from a Y source to a delta source, because we can then have a delta Y circuit, delta source Y load. We can also have a delta source delta load. But you'll find that those problems are not hard to do, because all you're going to do is change the source into an equivalent Y source, and then boom, you're right back to where you started in this problem. So follow me on to the next lesson. We'll talk about how to handle sources that are delta sources, how to make them into equivalent Y sources so we can do our balanced three-phase circuit analysis using the three-phase equivalent circuit.